In this video, we're going to utilize the fundamental theorem of algebra to find all possible zeros of a polynomial function. So in order to utilize the fundamental theorem of algebra, we need to actually know what it states. So on the screen here, you'll see both a theorem and a corollary. The theorem states that if f of x is a polynomial of degree n, where n is greater than 0, so this means a degree 1 polynomial or larger, then the equation f of x has at least one solution in the set of complex numbers. So remember, this f of x equals 0 is really saying that y equals 0. So this is when we're finding our zeros slash x intercepts. So essentially what this theorem states is that if your polynomial has a degree n where n is greater than 0, you will have at least one solution in the set of complex numbers. Now remember, complex numbers include both the numbers that are real and the numbers that are imaginary with the imaginary I. So basically what this theorem states and guarantees is that you will have at least one zero. Now, the corollary actually takes this one step further. It states that if f of x is a polynomial of degree n, where n is greater than 0, then this equation of f of x equals 0 has exactly n solutions. So here you can see, okay, if I had a degree 3, say n was 3, it's saying that I would have exactly 3 solutions. If n was 5, it's saying I would have exactly 5 solutions, as long as it's provided that each solution that is repeated twice is counted as 2 solutions, and each repeated solution that's there 3 times counted as 3 solutions, and etc. So as we solve polynomial functions today and find all of the zeros, we're going to keep the fundamental theorem of algebra in the back of our mind so we know exactly how many solutions we are looking for. So for the example you see on the screen, our goal is to find all solutions, both real and imaginary, for this polynomial function. Now remember, when we are finding the solutions here, we are finding all of the zeros. We're looking for when y is equal to 0. So essentially we're going to take this entire equation and set it equal to 0. Now as we begin, let's pay close attention to what we see contained in the problem. First, I see here that this polynomial is a degree 5. What this polynomial being degree 5 tells me is that I'm going to have 5 total solutions, as long as I count those double solutions as 2 and those triple solutions as 3, and so on and so forth. So that's the first detail there that I can see. Now, the second detail I see is that I have my polynomial, I have my a sub 0 value here, which is equal to -8, and I have my a sub n value here that is equal to 1. Now remember, while I know I have 5 total solutions here from using the fundamental theorem of algebra, I can also use that rational root theorem to find all potential rational zeros for this particular function. So remember, when we do this, we find all of the possible factors of a sub n, which in this case is just 1, and then all of the possible factors of 8 here, which are going to be 1, 2, 4, and 8. And then I take all of these p-values, which are the factors of a sub 0, and I divide them by my q-values, which are the factors of a sub n. So if I go through this process, I have 1 over 1, which equals 1, 2 over 1, which equals 2, 4 over 1, which equals 4, and 8 over 1, which equals 8. So my possible rational roots are the positive and negative versions of 1, 2, 4, and 8. So as I move forward to find all of the zeros for this particular polynomial function, I'm going to keep in mind that I have 5 total solutions, and I'm going to keep in mind that plus or minus 1, 2, 3, and 4 are all of my possible rational roots that can help me to get started. So what I've done here is I've taken my function and I have graphed it onto my coordinate plane. And what I notice here is that right off the bat, I can see that I'm crossing the x-axis in 2 spots. I'm crossing here at -1, 0, and I'm crossing here at 2, 0. So what I know from this is that I know that I can use those 2 values, test them out using synthetic division, and if they work, I can basically start rewriting my equation to hopefully get to a point where I can find all of my possible zeros. So remember, we are really solving this so it's set equal to 0. So that's our ultimate goal. And so what we're going to do to start is I'm going to use the x is equal to -1, 0, because I can see that I am hitting the x-axis at that point. So I take -1. I'm going to utilize synthetic division here. I have to make sure I add in my plus 0 x to the 4th. So I have 1, 0, 1, -2, -12, and -8. So I'm going to utilize synthetic division here. I start by bringing the 1 down, multiply it by my -1 here, so I get -1, add straight down, multiply it by -1, I get 1, add straight down, multiply it by -1, I get -2, add straight down, I get -4, multiply that by -1, I get a positive 4, add straight down, -8, multiply that by -1, it is 8, and then I have a 0. So what I can do at this point is I can rewrite my function to be, this tells me it's x plus 1, and then I have -8 as my constant. This is my x value, my x squared, my x to the 3rd, and my x to the 4th. So I have 1x to the 4th minus 1x cubed plus 2x squared minus 4x minus 8. So at this point, I'm going to focus here on this particular function. And I'm going to try to find another factor. Now, one thing that I notice on this particular graph is that it's not actually crossing at x equals -1. It is bouncing, which I know means that this particular root appears an even number of times, which means at a bare minimum, that particular root is appearing twice. So what I'm going to do a second time is I'm going to account for the fact that it's appearing 2 times. So I'm going to use synthetic division again on -1, but this time I'm going to utilize what's left here. So I have my synthetic division with 1, -1, 2, -4, and -8. So again, if I use synthetic division, I bring that straight down, I get 1, multiply it by -1, that's -1, add straight down, that's -2, multiply by -1, that's 2, add straight down, that's 4, multiply by -1, that's -4, add straight down, that's -8, multiply by -1, that is 8, add straight down, and I can see that that does in fact work. So now I can rewrite this equation again with that second -1. This is going to be my constant, my x squared, and my x cubed. So my new function here is f of x is equal to x plus 1, and then I have 1x cubed minus 2x squared plus 4x minus 8. So it's getting better, but I still haven't found all of my factors because I need to have a total of 5. So what I'm going to do at this point is I'm now going to utilize this x is equal to 2. So I'm going to utilize that and use synthetic division further. So I'm going to scroll down just a little bit here. So if I use synthetic division here, I have 2. And then I have my function here that I need to continue to divide. So I have 1, -2, 4, and -8. So if I utilize my synthetic division here, bring down the 1, multiply that by 2, that is 2. Add straight down, that's 0. 2 times 0 is 0. Add straight down, that is 4. 2 times 4 is 8. Add straight down, that is 0. So that does in fact work. So what I have left here is I have a constant value, and I have no x value because there's a 0, and then I have my x squared. So my new function right now is f of x equals x plus 1, I then have this one as x minus 2 because it's the opposite. And then what I have left here is x squared plus 4. So what's difficult now is that I don't really have a way to use synthetic division to factor this further because I've exhausted all of my rational roots. So I don't have any numbers that I see where I am crossing the x-intercept that I can actually put into here to help simplify this last piece a little bit further. So what we're going to have to do with this last piece is we're going to have to set it equal to 0 and solve. So here we have x squared plus 4 is equal to 0. And we need to figure out what x values make that equal to 0. Now, you have a couple of options here. Factoring is not an option because it's not a difference of squares, it's a sum of squares, so that one's out. But I could use the quadratic formula because I have an a and a c value and my b value would be 0. But I can also use the square root strategy that we talked about previously, where we get the squared piece alone and then we square root each side. So that's what I'm going to utilize for this particular example. So here I'm going to start by subtracting 4 on each side, and I end up with x squared is equal to negative 4. Then from here, I'm going to get the x alone by square rooting each side. Now because I am square rooting a squared, I know I need to include my plus or minus and the square root of negative 4. So I have x equals plus or minus the square root of negative 4. Now, I have to be careful here because I need to make sure that I am fully simplifying every single square root that I have. And what I realize here is I can split this up into the square root of negative 1 and the square root of 4. And what I remember previously is that the square root of negative 1 is I, and then I know the square root of 4 is 4. So what we find is that x equals the plus or minus version of 2i. So what I've ultimately found here from this equation and using my knowledge of how rational roots work, the graph, and synthetic division, is I have found all of my zeros. So all 5 of my zeros for this function. My first one is x is negative 1, y is 0, and this one is a double and counts twice. I then have 2, 0 as another option, and then I have 2i, 0, and negative 2i, 0. So I have a total of 4 zeros. 2 of them are real zeros, and I can see them physically on my graph, and 2 of them are imaginary zeros. So they're solutions to my particular equation, but I won't necessarily be able to physically see them on my graph.